16 AP Mechanics, multiple choice. This is probably the trickiest of the published test. I think this one definitely is harder than 2014 and 15 and some of the other ones I've already reviewed. So let's get started. A projectile is launched with a speed, that's V naught, of 40 meters per second at an angle of 30 degrees. And again, they gave you this angle of 30 because back in the day you didn't get a calculator. And so if you think about special right triangles, if you launch something at 30 degrees, then if the hypotenuse is 40, that means vertically it's at 20. So this V naught sine theta component, the vertical velocity, we do know is 20. And so we're launching from the ground at 20 for t, and then we land 3 seconds later. So really all you're doing is plugging in 3 seconds into time and figuring out the height. So if you look down here, launching at 20 for 3 seconds minus a 1/2 g, and I'm using 10 to make it easy, 3 squared, you end up just getting 15. So then it must, if it landed here in 3 seconds, then that height must be exactly 15 meters. Again, think projectile motion, and they did use some special right triangles. You now have your calculator, and so you could have just put in 40 sine 30 times 3, or you could hit this and you could graph it at 3. It doesn't really matter. All right, this is kind of a moving reference frame, or I should say an accelerated reference frame, but we have this thing, and this car is moving, specifically accelerating to the right, and it's going to make this object swing back and kind of hold that position. Well, when it holds that position, then we know that all these forces have to be balanced. And so what happens is you have t cosine theta is remember the angles with respect to the vertical. So t cosine theta vertically supports mg, which means that t equals mg over cosine theta. And then horizontally, we know that t sine theta, that component of the tension, that must be accelerating the mass at that rate. And so you can take mg over cosine theta and put it in for t, and you can get this equation. You can cancel the masses, and then based on the angle of tan 37, you can get an approximation of the acceleration. So we are talking about a free-falling object under the Earth. Again, we're near the surface of the Earth, so we don't have to worry about big boy gravity or anything, and there's no drag, and so the speed of an object increases by 9.8 meters per second every second. That is the definition of g. 9.8 meters per second squared is gravity pulling you down and increasing your speed down by 9.8 meters per second every second that's in the air. Remember, you're looking at a position versus time graph. So the slope here is velocity. So the speed, they're being a little tricky, right? Speed is the magnitude of velocity. So the slope is getting smaller and smaller and smaller, because this is a big negative slope, and then this is like a -1 slope, and then this is even less than that. So the speed itself is decreasing, but we are moving to the right. All right, this is a little calculus, so they give you some force as a function of time, and we know that the impulse, anytime they want to know the magnitude of the change in momentum, that's this. We often can look at the area under the curve. If it's algebra, meaning it's a constant force, we can just do force times that time period. But if not, then we do have to do calculus. And so we have to accumulate the force over time. So I'm integrating alpha t minus beta t squared. And I just do power rule, and then I evaluate it from 0 to 0.1. And I get that amount. That's the change in momentum, which is the impulse. The units would be the units of momentum, which is just kilogram meter per second, or often with impulses, they use Newton seconds, because it's applying a force for a certain amount of time period, causing a change in momentum. It's just classic center mass. You have two different spheres located a distance L apart, and they want to find the center mass. And so you take the mass times where it is, the mass times where it is, divided by the total mass to find then the average position of that system. All right, there's no friction there, so we don't have to worry about that. So the only thing that's actually doing work, and the work is changing the kinetic energy, is the horizontal force. Remember, work, this right there, work being F times D, that really is a dot product. The only thing that does work is the force that's in the same direction as the displacement. And so we're really talking about F cosine theta times d. So 15 cosine 37 times d is the work done, and the work done then equals the change in kinetic energy. The magnitude of the force on the block, so then we do have to look at the vertical components. We have the normal force up, we have mg down, and then we have this applied force down, right? We're pushing this box to the right, but we're also pushing it down. And so we have to solve that for the normal force. This one is rotating at a constant speed, which means there's no net torque on this thing. I mean, it's rotating, but something got it rotating, and then these forces are applied. But if it's constant angular speed, there's no net torque, which means the torques have to balance. And so there's a torque caused by that force, that one would want to make it spin counterclockwise, and then the torque caused by this one would want to make it spin clockwise. This has 3 times the lever arm, so then F1 would have to be 3 times the force to make it balanced. Again, that's kind of what I'm doing down here. I'm setting the 2 torques equal to each other, 3 times the force, a third of the lever arm, or vice versa. We've done this one before. This is just a car turning, and again, we're talking about a car turning in a circle. Thus, there must be some inward force, and in this case, the inward force is the force of friction, which is mu n, and in this case, it's mu mg, and then that causes the mass to experience circular motion, and you can solve for whatever variable they want you to. In this case, it looks like they want mu. Here's our banked curve, and there's a free body diagram. Once we have the bank there, then the normal force goes up and inward. Force of friction goes down and inward. So you can see that both the normal force and the frictional force have inward pieces to it. And so the idea of what the banked curve does is that it allows the normal force to help move it into a circle. The normal force generally is just straight up, but when you have a banked curve, now the normal force, since it's normal, perpendicular to the surface is now banked, the normal force does actually point left, and in this case, left is inward. Thus, the normal force helps you move in a circle. This is really wordy, but it's not actually difficult at all, but it is, because there's just so much information here. They're just trying to trick you. So basically, at the beginning, you have a rope here and a rope here, and the pivot's kind of there. You're like, oh, well, each rope, if the one rope is 150, well, the other rope has to be 150. Otherwise, the thing would rotate, right? Because the whole thing is that it's balanced. Okay? Then you take this rope and you move it to R. But when it's at R, it's got to be like this. It's got to be bigger, because now look at its lever arm. Its lever arm is D, and this is 2D, and so then the forces have to be in that same ratio. It's a 2-to-1 distance, so it's got to be a 2-to-1 force. The forces themselves still have to add up to 300, because the board itself, well, that's still 300. I'm going to say that again. They told you that the board wasn't rotating, and they told you that the left one was 150. But that also made then the right force have to be 150. So now we know that the board is 300. We then move this rope over here, we move it to R. Well, now that it's a position R, it's D away from C, the center mass of the board, and this one's 2D away. This one's got twice the lever arm, and this one's got, so it's got to have then half of the force. So now we're going to break it up into a 2-to-1. So take that 300 and break it into a 2-to-1, and you can see that it's 200 and 100. Okay? We've seen this before. This is a potential energy function, and they're going to ask you about forces or accelerations. In this case, they want to know when the object is moved a distance 10 from, what's the magnitude of the force associated? So they're just asking you to kind of just plug in here. It started at 30, so moving 10, now it's at 20. And so what we do is we look at the potential energy function. We know that the force is the negative derivative. So we take the negative derivative of this guy. There you go. There's the negative derivative. And then we plug in 20. Again, it tells us that it moves left when released. Right? The force has to be negative. Okay? Again, it just wants to know the magnitude, so I guess we didn't even care about the negative sign, but we are just plugging in 20 for x. A student pushes a box. There is friction. Anytime they say rough, they are talking about friction. If they say smooth, that means there's no friction. So the amount of work we did is 100. The amount dissipated by friction is 40. So then what was the leftover? Well, the leftover work must have increased the kinetic energy. So all we're doing is 100 minus 40. Super quick. All right, they've asked this one before. They've asked it with ropes. And they said which rope had the greatest tension. Here they replaced the ropes by springs, and they want to know which spring is stretched the most. Again, think about it. This spring is required to pull the entire system. That spring has to accelerate all these. That spring doesn't even know that these springs exist. These boxes might as well just be connected by bolts. That spring has to pull all 6 M's. That spring, the middle one, not only has to pull these 4, and that last one not only has to be responsible to pull the 2. Again, A is for sure going to stretch the most because it's got the biggest force, because it's required to to accelerate all 6 M's. So this is Pythagorean theorem. Think about we're throwing something like this. That's this piece, and it won't change. That's just V naught cosine theta. And then there's some vertical speed, but the vertical speed is going to be a function of time. It's going to be how fast you were starting vertically, and then what gravity did to it. So this equation here is just the Pythagorean theorem. We know that the speed as a function of time is going to be the Pythagorean theorem of the horizontal velocity and the vertical velocity. The vertical velocity is just a function of time. I actually really like this question. This next one, I think I went too far on it because it just wants to know the maximum positive velocity. So they gave you this position function. Just go ahead and take a derivative and then you can stop. You can see right there that the biggest that velocity ever is 4, because it's 4 minus 18t squared. I don't actually know why I did that. That was irrelevant, right? The maximum velocity is just the original velocity, which is 4. 2 balls given the same mass and diameter, that's all worthless, blah, blah, blah. They collide with the ground, so we know we're talking about momentum with the collision, and ball A bounces higher. Well, that must mean that A got a bigger impulse exerted by the floor. An impulse is the change in that guy's momentum, which means it's a change in its velocity because mass isn't changing here. And so the only way you bounce higher is if you had a higher velocity, which means you had a bigger delta V from the floor, which means the floor gave you a bigger impulse. This is a collision. This is just standard collision, so we conserve momentum. This is me conserving momentum. I really should have wrote down P1 equals P2. This is originally what's happening. The original momentum is just mv. Afterwards, they tell you this. Make sure, since they tell you it's going west, that we do use a negative sign there, and then we can find what that guy is. All right, we're just solving for what happened to the other box. So I know this is a word that we obviously wouldn't use in class, but the AP does use it and has used it before. I would guess they will stop using it. But that just means that is a resistive force. That force is just going to slow something down. And in this case, it's just torque equals I alpha, and they want to know the angular acceleration. We know that the torque is caused by the force and the lever arm, and it does say it's applied tangentially. So that just means there's no angle associated, or it means we don't have to worry about the angle because it's 90 degrees. Remember, a torque is a force, a lever arm, and the sine of the angle between them. So the force is just F, the lever arm is R, that's the torque, and that causes I alpha, and you just divide by I and find alpha. So actually pretty easy when you think about it. Same thing here. This force is slowing something down. It's changing the mechanical energy. So what's the reduction or the loss of mechanical energy? It's just the work done, and the work done is equal to I 1/2 I omega squared. Okay, so we drop something, and then we drop another one 1 second later. And again, you got to think about, they're both going to be accelerating at the same rate. I get that. But the first one will always be moving faster. So when the second one gets dropped, the first one is already going 9.8 meters per second. And then after another second, at the end of that second, the first one's now going 19.6 meters per second, and the first one's going 9.8 meters per second. But if the second one is always moving faster, it will always keep separating more and more and more. And so the distance between them will increase. The second one will always be moving faster. This one's really wordy, but it's just how we add vectors. Right? This is like a current. The river is going this way. The boat is going this way. When you enter that thing, now you're going like this. And what represents the velocity of the boat? You would add those vectors together. Now, we know how to add vectors. Well, we'd have to add horizontal components with vertical components, but that's the notation of just adding vectors. That's the boat relative to the water, and the boat relative to the land, and the boat's velocity relative to the river. All right, this is kind of a graph thing. Remember, force versus distance or displacement, that's going to be work. Force versus time, then the area is impulse. So this is a work question, and it wants to know the work done for the first 10 seconds. So we just had to find that area in there. So the area, I don't know why that's keep making that black, but the area in there is 75. So then the work done is 75. And then this one's a little tricky. It wants to know the kinetic energy of the 2 kilogram object when D equals 20 meters. Okay, so think about this again. Look at this whole thing. This here equals this here. So whatever this did, this just took it away. So the energy it has at 20 is the exact same as it had at 5. I'm going to say that again. The force did some positive work on this stuff, on this object, but then it did some negative work on this stuff, meaning it was slowing it down. From 0 to 5, it did some stuff. It did 25 joules worth. But for then from 5 to 20, whatever it did here in blue, it got negated by this blue. So the energy it has at 20 is identical to the energy it had at 5. And that's what that question is saying. It's a really weird question, I think, but it's just looking at the symmetry of those two things. This is a stupid question. Don't let it trick you. It says right here, an astronaut weighs 600 newtons on Earth, which means the mass on Earth is 60 kilograms. But that means the mass anywhere in the universe is 60 kilograms. Remember, mass is not going to change. This one is looking at big boy gravity. We're looking at the kinetic energy when it hits the surface here. And we know the kinetic energy is going to come from potential. So this is just me saying E1 equals E2. And the change in potential, remember, big boy is just negative GMM over R. So this is the original kinetic energy, negative GMM over R minus negative GMM over R when it hits the surface of the Earth. That change in potential, I set equal to kinetic, and I solve for V. So it's a little more just working in the abstract and algebra. But again, it really is just conservation of energy. It's just mgh equals 1/2 mv squared. It's just the big boy version. So when it's at its highest point right there, horizontally, still going V naught cosine theta. It's going V naught cosine theta the entire time. Vertical velocity is 0, so the velocity is just the horizontal piece. And acceleration, well, gravity never turned off. Gravity is always 9.8, always pointed down the entire time. This is just a conservation of energy situation. We know there's no kinetic going on. There's going to be a loss of potential energy, and that potential energy is going to stretch the spring. The height change, remember, is d sine theta. It slides down the ramp a distance d, but it actually only falls vertically amount d sine theta. So this is just E1 equals E2, conserve energy, potential goes to elastic. This is simple harmonic motion. They give you this. We know we can take two derivatives of the position to find the acceleration. So then the acceleration is going to be an A omega squared, cosine omega t with the negative sign out in front. And so if we have acceleration, remember we know acceleration is this a omega squared. If we just multiply by mass, we can turn it into force. Again, I get it. They're kind of trying to trick you. They give you position and they want force, but you know with position, you can find velocity and acceleration, but with acceleration, you can multiply by mass to find force. They want the total mechanical energy. This is something we showed in class. That's always what a satellite's total energy will be. The total energy is a combination of its potential energy, negative g mm over r, and its kinetic energy. But if a satellite is in stable circular orbit, we know that this, the square root of that, is the orbital velocity. And so if you just square it, you get that. Plug that in for v. These two terms will then add together to give you this. And so that's what you do. This and this is the same thing. The big M and little m is just the mass of the Earth and the mass of the moon. Remember, the moon is orbiting around the Earth, and gravity is causing it. And so you could just, this is me just deriving the velocity of the moon, but that is the orbital velocity formula. The square root of that is probably what you hopefully have memorized. All right, this one's, there's your escape velocity formula. You could derive it using energy if you want. And what they're saying is you are going to launch it now at twice the escape speed, and then you want to know what happens. Okay, so here's our escape formula. This is just conservation of energy. This is E1 equals E2. The original energy is a potential, negative g mm over r, plus the kinetic, and you're going to double it. So you're going to double this velocity, but then you're going to square it, so you're going to create this factor of 4 there. So then when you add these together, you get this. You set it equal to 1/2 mv squared. The m's cancel, the little m's, and then you do that. And you get this. You're like, oh, wait a sec, that's not the answer. But then you got to compare. And you're like, how does this compare to this? Well, this guy compared to that guy, this is the square root of 3 times bigger than that. So that's your answer. This is a pretty difficult double, triple question. You got to really think things through. Lots of algebra, escape velocity, energy, and even at the end, you're like, how do I compare? Well, you got to compare how much bigger the square root of 6 is compared to the square root of 2. Well, it's the square root of 3 times bigger. Blocks, there's no friction, and again, it's one of those that are trying to trick you. That block and that block start at the same height. Thus, they're going the same velocity here and here because they've got the same potential energy, so they have the same kinetic energy, and that same kinetic energy is going to still slide the same amount. Okay? Conservation of energy, same distances. This one, I should have crossed off that too. None of these matter, right? This is like taking a board and putting a box there, and we lift it up. And then eventually, gravity down the ramp overcomes friction up the ramp, and it starts to slide. And the only thing that matters is the coefficient of friction. That's the only thing that matters. The mass cancels out. The cross-sectional area of what's the contact area, the contact area doesn't matter either. It's all about just what mu is. And the last one, this is like a unit analysis thing. So look at this equation. This side is in meters. It's a velocity times a time. So that's a meter per second times a second, which means that term there is in meters. Well, 4 times x. Well, x is in meters. All of these are in meters, so that means this guy has to also be in meters. Well, the only way a bt squared can be in meters is if b itself is a meter per second squared. The second squared has to cancel with the t squared, making it meters. Thus, b has to be some sort of like acceleration piece. I do think that test was a little trickier than the other ones, but they're all just a little bit different. Absolutely worth reviewing all those questions.